join the real time session, then you may view the recorded version. Okay. If you have any question regarding the syllabus or the unit materials or any questions on the course assessment, then you may WhatsApp to my number, and then I will reply. Okay. You may contact me 24/7, meaning that tak ada time limit. But then give me some grace period to reply, because sometimes I'm teaching dekat university, or I in the middle of meetings ke, and sometimes ada juga I don't have the materials with me, so I can't straight away reply. So once I have the chance to respond to the students, and then I will reply lah regarding the query. Okay. Same goes before you submit the course assessment, then you can before you submit, then you may verify with me first. Okay, nak check ke kalau ada salah, or is there any rooms for correction, then you may show to me first before you submit in the system. Okay, for our class digital electronics, our CC is Dr. Hazri. Okay, you guys can see my screen? Boleh nampak tak? Okay, our CC boleh ya. Our CC is Dr. Hazri. If you need any extension for the course assessment, please apply in the system. Okay, must get approval from Dr. Hazri first. Okay, for the extension lah. Okay, so for our class full house, 35 students. 35 ni meaning that kita full lah. Okay, so for this digital electronics, previously I think dalam 1 or 2 years back, digital electronics is we have 5 credit hours. It is, the code is 206. Dulu kita ada 5 credit hours, code dia 206, and we have 5 units to cover. Meaning that ada 5 tutorial lah. Okay, and sekarang ni WOU split the 5 credit hours digital electronics to 2 mainly course. Okay, one is digital electronics 3 credit hours, and the next one is digital circuit design. Okay, digital electronics we cover unit 1 to 3, and circuit design is 4 and 5. Okay, meaning that this digital electronics is prerequisite subjects to take the digital circuit design. Okay, so for this semester I ajar digital electronics and also digital circuit design lah. Okay. For this digital electronics, we have 3 main unit. Okay, the first one is on the introduction to number system and logic gates. Okay, we will cover this today. Okay, what is logic gate, the gate universality. Okay, and unit 2 is on the Boolean algebra. Okay, this is for tutorial 2 lah. Okay, on the operations of the Boolean numbers, okay, arithmetic circuit, and the canonical form. Okay, and unit 3 is on the combinational logic design. It is more on the minimization of the Boolean function. Okay, and what is the K-map technique? Okay, this one will be discussed in unit 3. Okay, throughout this semester we have course assessment 1 and 2, and we will have the online examination, online final examination lah, because semester lepas kita ada final exam, but then it is online. So I think for this semester pun WOU akan buat online lah. Okay, for online dia akan cover the whole unit 1, 2 and 3. Okay. And this is our slide for today. I have attached here dekat sini slide for this unit 1. Kalau you guys belum ada, then boleh download from here. Okay, for this introduction to number system and logic gates, we have 4 subtopics. First is numbering system. Second is on the arithmetic in different number system. Okay, the third one is on the representation of negative number. This one we will discuss on the complements and second complements. Okay, and finally is on the logic gates. Okay. Sorry, and another one we have gate versatility. Okay, another one we have gate versatility. All right. For the numbering system, okay, now we in the number system we already knew on the decimal number 1, which is 1 to 10. Okay, but then in computer we only have 2 conditions or 2 states, on and off. Okay, also we can represent in digit 1 and 0, or we can say it is high or low. Okay, with the convenience of the 10 digits which serve human well when performing the calculations. Okay, the computer operates differently. Okay, every microprocessor in a computer is made of million miniature transistors that can be turned on and off like switches lah. Okay, transistor we can use as switches. Okay, every which we for the switches on and off we associate with condition of 1 and 2 or high and low. Okay, this is representation of the binary number system. Okay, in computing terminology, we also refers to the digit zeros and 1 bits. Okay, microprocessors does all the computations. In fact, the mathematics surrounding in binary system allows the explosion of the information we see today, and also we use in the communication technology. Okay, we will learn different number system and how they are formally defined, especially the binary number system. Okay, this is the most fundamental level. The digital electronics uses the binary number system exclusively. Hence, this is important. Okay, for us, while the binary system is fine with digital machine, we prefer to count in decimal system. So we will discuss on how to convert between binary to decimal. Okay, example here we have this value, and this is for the binary number format. Okay, to the power of 5, 4, 3, 2 and 1. Okay. Okay, the format of the binary, this is for the decimal 10 to the power of 5. This is in binary 2 to the power of 5. This is according to how many bits that we use lah. Okay, this one point minus 1, minus 2, minus 3 and minus 4. Okay, this is responding weight. Okay, 2 to the power of 5 we get 32. If 2 to the power of minus 1, this is the value. Okay, and minus 4 dapat inilah. Alright. Okay, each digit has a position with follows for the position dia lah. 1, 2, 3, 4, 5. Same goes with the decimal. Okay, the digit value, how to get the digit value, multiply with the base position. Okay, position number is position to the left side of decimal point, and position number is negative at the right side of the decimal point. This one is negative for the decimal point. Okay, positive is at the left side. Okay. Okay, for like here we have 476.23. Okay, this is base 10. Then we can write this term lah. Okay, this is for y 10 to the power of 2 because here 0, 1, 2. Okay, the position is 0, 1, 2, 0, 1 and 2. Okay, so 4 multiplied with 10. This is the base. Okay, and this is the position. 7 and 6. Okay, how about the decimal point? Okay, for the decimal point, decimal number here, minus 1 and minus 2. Okay, minus 1 and minus 2 because we start with minus 1 and minus 2, minus 3 and so on and so forth lah. Okay, this is for decimal number. This one is for decimal, sorry, this one is for binary number. Same concept for binary number, but then we only change the base number here because this is in binary. So the base going to be 2 lah. Okay, 0, 1, 2, 3. 0, 1, 2, 3. Minus 1 and minus 2. So this is how to do the conversion, okay, from the binary and decimal. Okay. Okay, let's use the previous binary number example. We have 1011.01. Okay, this is in base 2 and this is weight value. Weight value is the actual value. Okay. Okay, the weight value of the digits for binary number. This is the decimal point starting from 0, 1, 2, 3, minus 1 and minus 2. So this is we get the binary number. Okay. Okay, the conversion of a binary number to decimal number we can achieve based on the digit position and weight value of each digit, and then we can sum up all the value. Let's say we have 1011.01 base 2. Okay, we write this one lah, yang ini, this one, and this is the decimal point. So we can sum up all these value. Okay. If you sum up all this, then we can get 11.25 in base 10. Meaning that 1011.01 base 2 is equivalent to 11.25 base 10. Alright? Okay, to convert an integral decimal number to its binary equivalent, we have to repeatedly divide the integral decimal number by 2, okay, to the base of binary system. Okay. For fractional number, it is done by first subtracting 0.5 from the fractional number and followed by subtracting 0.25, 0.125, 0.625. Why? Because here, follow this concept, 0.5, 0.25, 125, 0.0625. Okay, follow this concept. Okay, until there is no remainder or there is no desired binary points has reached. Okay. During the process of subtracting, if the remaining fractional number is less than subtract, okay, a number to be subtracted from another number. Okay, for the subtract, 0 is given, and otherwise we will set to 1. Okay. Later we will see an example for fractional number conversion. It is done by we first subtract like this one tadi lah. Okay, starting from 0.5 to 5, 1 to 5, 0.06 to 5. Okay, and we give 1 or 0. Okay. For example, we have this value 121.625. Okay, in the base of 10. Okay, first we take this digit number 1 to 1. Okay, for 1 to 1, we want to convert into base 2. Okay. Okay, we want to get to base 2. Okay, first we take the 1 to 1 divided by 2, then we get 60. Okay, so the remainder is 1 and 60 divided by 2 becomes 0, get 30. 15 divided by 2, we have remainder. Now we also have remainder. 30 divided by 2, we have 1 remainder, and 1 divided by 2 is 0.5 kan. So there is 1 here, remainder 1. Okay, so this is binary code taking from bottom to the top. 1 1 1 1 0 0 1. Okay, from bottom to the top. Okay, this is in binary. Okay, not settled yet. Only for 1 to 1. Okay, kita baru buat yang this 1 to 1. Okay. Next, we want to do for 0.625. Okay, for this one. Okay, for fractional number, it is done by first we subtract to 0.25. Okay, then we subtract to 0.25, then subtract to 0.125, and followed by 0.0625. Okay, so the first one we subtract 0.5. Okay, we have this with one remainder. So take this value minus 0.25. It is less. If it is less than 0, then we make it 0. Okay. Followed by 0.125. And finally this one here is 0.0625. Okay, 0.0625. Okay, so we take from 1010. For this one, take from the top to the bottom. Okay, for the binary code, for decimal, 0.101. Base 2. So we take 0, we take from the this one 1111.101. This one tak perlu ambil. Okay, to the base of 2. So meaning that we have 121.625 base 10 equivalent to 1111.001.101 base 2. Right? So that's for decimal and binary number. If you guys want to try to do for let's say 56 to the base of 10. What is the value for binary number? Okay, let's say 56. 56 base decimal. What is the value in binary? Okay, the answer should be 111000. Okay, you can try to do 111000. Alright. Next, we go for next number system. It is octal code system. Octal is base 8. Okay, octal number has base of 8. It has 8 digit. We can represent in 3 digit binary number. Okay, 000 or 111 or 0 up until 7 in decimal system. Okay, for example, we have 721 base 8 represent as 1110100001. Okay, this one is 7111. This one is for bit 2, 010 bit 2. Okay, to the base of 0, base 1 and base 2. Okay, in binary. And 1 is 001. Okay, this is in binary system with 8 digit. Okay, the system is not widely used in microcomputer system when the machine language programming is required. Okay, for example, another example, we have okay, let's say 721 base 8. Okay, The equivalent number in base 10, okay, 721 base 8, okay, what is the value in base 10? Okay, it will be 465 to the base of 10. How to get it? Okay, 7 multiply with 8 to the power of 2. Why? Because it is 0, 1, 2. Remember? 8 to the power of 0, to the power of 1, to the power of 2. So 7 multiply with 8 to the power of 2 plus 2 multiply with 8 to the power of 1 and plus 1 multiply with 8 power of 0. Okay. So 7 darab 8 kuasa 2 tambah 2 darab 8 kuasa 1 tambah 1 darab 8 kuasa 0. It will be 448 plus 16 plus 1. Okay, so summation of all 448 plus 16 plus 1, 448 tambah 16 tambah 1 is going to be 465, okay, to the base of 10. Meaning that 721 base 8 sama dengan 465 base 10. Okay, this is for octal and decimal lah. If you want to convert from octal to decimal. Okay, from octal, it has to go to decimal first and then go to binary. Okay, if you want to convert to binary lah. Okay, let's say for example, another example, what value? Okay, let's say 563. Okay, we have, if you have pens with you, you may boleh sketch, boleh tulis ya, note down. Let's say we have 563 base 8. Okay, sama je macam ni. Ini adalah 721. Now we change to 563 base 8. Okay, we change to decimal first. How? 5 multiply with 8 to the power of 2 because 563, yeah. And plus with 6 multiply with 8 to the power of 1 and plus with 3 multiply 8 to the power of 0. Okay, so meaning that 5 darab 8 kuasa 2 tambah 6 darab 8 kuasa 1 tambah 3 darab 8 kuasa 0 is going to be 320 plus 48 plus 3. Okay, and equivalent to 371 10. Okay, 371 base 10. 371 base 10. Okay, 3, let's say 371, this is yang kecil ni base 10. Also equivalent to kalau 3, meaning that 001, 7111, okay, 1001. Okay, in the binary number lah. Okay, for binary number. Okay, we have okay, this is in octal, binary and the number decimal. Okay, if in octal 007, so meaning that in binary 00, this is 7, decimal is 7. Okay, if it is 010, it is 0, 1 and 0. Okay, in decimal 010 is going to be 8. Okay. Okay, for if 011, dia jadi macam ni, 011. Okay, why it is 8? Because it is 2 to the power of 0, 1, 2, 3. Meaning that here, 2 darab 1 darab 2 kuasa 3. If 2 cube 2 kuasa 3, dia akan jadi 8 lah. Okay, same goes untuk yang ini. 2 kuasa 3 tambah dengan 2 kuasa 0. Okay, 2 to the power of 0 and this is 2 to the power of 3. So we get 9. Okay, for 111, 111. So if we change, we get this 73. Okay, this one is 563. Equivalent to this value for binary number and this is in decimal base. Alright. Okay, this is for octal, binary and the decimal. Next we have hexadecimal. For hexadecimal number, it has base of 16. Okay, it has 6 digit which we represent in 4 digit binary number. Okay, 000 or throughout the 111. Also we can have 0 from 0 starting to 0 to 9, okay, and A, B, C, D, and E, and F. Okay, A is 10, 11, 12, 13, 14, 15. Okay, because we end with 9, this is considered as 10, 11, 12, 13, 14, and 15. Okay. For hexadecimal number ABC1, we can write in base 16 or write as H here. For this base 16 hexadecimal, widely used in microcomputer system when the machine language programming is required. Tapi tak banyak sangat lah, okay, for the hexadecimal. Okay. Let's say if we have 1A in hexadecimal, so this is for bit 1 and this is for bit A. Ini sama saja macam yang ni tadi, like this one. Okay, this is bit 1 and this is bit A. A, remember, it is equivalent to 10. A is equivalent to 10. So, how to get this? 2 to the power of 0, 1, 2, 3. 2 kuasa 0, 2 kuasa 1, 2 kuasa 2, 2 kuasa 3. So, if 2 kuasa 0, 1, 2, 3. So, we can get this value lah. Okay. 10 maksudnya. Okay, this is for 1A, and if we want to convert into decimal, tambah je lah semua and we get this 26. Okay, so if it is 3B, this is in binary system, B is 11. Remember, it is 11 and this is 3. Okay, and 51 biasa saja for 6A. Okay, this is A is 10, 11. This is 10, 11, this is 12 lah. C is 12. Okay, meaning 12 with 10. Okay, and FF is 15. Okay, for FF. Okay, this is all high bits. Okay, semua satu. Okay, FF equivalent to 255 decimal number. Okay. Do you guys know how to get this 26? How to get this 26? Okay. Since it is in hexadecimal code for hexadecimal base, then for this one, this is 1. So 1 darab 16 kuasa 1 and tambah dengan 10, since it is here kat sini is 10, 10 darab 16 kuasa 0. So 1 darab 16 kuasa 1 tambah 10 darab 16 kuasa 0, then we can get 26. Okay. Same goes here, 3 darab dengan 16 kuasa 1 tambah dengan 11 darab dengan 16 kuasa 0. Okay. If here, for this one, 255, okay, 15 multiply with 16, 15 multiply with 16 plus 15 multiply with 16 to the power of 0. Okay, meaning that 15 darab 16 kuasa 1 tambah 15 darab 16 kuasa 0. Okay, dia akan dapat 255. So that's how to get conversion from hexadecimal number. Okay, in base 16 and to the binary and to decimal number. Okay. Next we go to binary coded decimal system. Okay, for binary coded decimal or BCD is a way to express each of the decimal digit with a binary code. Okay, we have only 10 codes which is similar to the decimal system. Example, we have 8421 codes is a type of BCD, binary code decimal. Okay, it has 4-bit binary code for each digits from 000 through the 1000, which we start with 0 to the base of 10 through the 9 to the base of 10. It is used for visual display that we can be understood by human being that the decimal number system being used. Okay, Okay, since each digit has 4 binary codes, then 1010 through the 1111 are not valid for this code decimal, meaning that we can't use 1010. Okay, let's see. For example, here we have in decimal. Okay, in decimal base 10, 15. So this is binary code decimal. The binary coded decimal addition is the same as the decimal addition, except that the difference is invalid when its value is between 0101 and 1111. If the difference is in the invalid range, then a binary 6 or which 1010 has to be added to the summation. We can say that this would generate a carry bit which needs to be added to the next highest significant digit. If the value in the next highest significant digit has invalid number, then the binary 6 has to be added. This procedure has to be done until all digit has valid number. Ini kita akan tambahlah for each of the step. If the summation is in between 000 and 1001, then the summation remains unchanged. Okay. So that's for binary coded decimal BCD. Okay, next we have gray code. Okay, gray code is a unit distance code. It is unweighted. It is not an arithmetic code. The binary to gray code conversion we can achieve by first we begin with most significant bit of the binary number and then write the value of the most significant bit as the most significant bit of gray code. In the conventional binary misalignment encoder, it is difficult to distinguish which, for example, which we have photosensors is misaligned since both the sensor adjacent to each other which are unblocked. However, for the case of when we use the gray code misalignment encoder, only one sensor is clearly identified. That is important of the gray code. That's for first subject. The next is arithmetic in this full number system. Okay, this is to perform the arithmetic operation in binary, octal, hexadecimal system. Okay, we have learned on how the number system were established, like the binary number system, and how each digit is represented in decimal number system from its position and the base number. That's important lah. We have to know the position and the base number. Then we have learnt on the various type of number system, like we have octal number system and hexadecimal and so on lah. It has included the study of the conversion of number of any of the system to any number system. Okay, be from the binary to decimal system and vice versa. We have binary to decimal or decimal to binary. Okay, or conversion of number from binary to octal or hexadecimal and binary coded, okay, and vice versa. Okay, there is so much other coding system being used for computer systems, such as we have ASCII code, ASCII 2 code, and ASCII ASCII extended code. That's some more example lah for the coding number. Okay, for the binary, we can do addition or subtraction. Okay, there are 4 basic rules in binary system, as we can see in this table. Okay, the first 3 rules are simple. Okay, the fourth is different from decimal. When we add 2 first value together in binary, then we generate a carry bit 1 to the next column, since the binary system only has 2 digits. Okay, for rule number 1, 0 add with 0 jadi 0, 0 tambah 1 jadi 1, 1 tambah 0 jadi 1. What happen if we add 1 by 1? 1 tambah 1 is not going to be 2. Okay. Okay, 1 tambah 1 is going to be 0, but we carry 1 bit to the next column. For example, here we have 1, 1. Okay, we add with 1, 0. Both is in base 2 binary. Okay, so 1, 0. Jadi 1, 1 and 1, it becomes 0, but we have carry 1 bit here. Okay, so the answer will be 101. Okay, this one is for addition. Say if we have to add 1, 1, 1, kalau ada 3 1, this one we have only 2, 1 by 1. 1 tambah 1 dia akan jadi 0, carry 1 bit. If we have to add 1, 1, 1, it will become here 1. 1 tambah 1 tambah 1 dia akan jadi 1, but we have to carry 1 bit. Okay, we have to carry 1 bit. Itu kalau 1, 1, 1. Alright. Next, kita tengok the subtraction. We have 4 basic rules. Sama juga 0, subtract by 0. 1 minus 1 jadi 0. 1 minus 0 is become 1. Okay. The first 3 rules sama je. Okay. The fourth rules is may appear a little strange here. Okay, what happened here is we borrow from another column. Okay, 0 minus 1, we borrow 1 from another column. When we borrow 1, dia akan jadi 1, 0. So if 1, 0 minus 1, it will become 1. Okay. This yang addition, dia akan carry 1 bit to another column. For subtraction, it will borrow 1 bit from another column. So it will become 1, 0. 1, 0 minus 1, it will become 1. Okay. Let's see an example. 1, 1, 1, 1 minus 1, 1, 0. 1 minus 0, 0. 1 minus 1. Okay, 1 minus 1 is 1. 1 minus 1 is 1. Sama juga. And 1 minus 0, this one is 0. Dia akan jadi 0. This one here, 1 minus 1 is 0. Sini salah ni. Okay. 1 minus 1 is 0. Follow this rule. 1 minus 1 is 0. Okay. Next, we go for addition and subtraction in octal and hexadecimal. Okay, same goes here. Very similar to the addition and subtraction. We want to add 3 to 6 in base of 8. Okay, 3 to 6 in the base of 8. So we will get 11 in base of 8. Okay. It will not become 9 because it is base 8. Okay, base 8. Carry, this one is carry 1 bit. That is why we have kat sini lah. Okay. 3 tambah 6, it is actually 9, but then we only have value up until 7 to the base of 8. So kita carry 1 here. Okay. Why? Because it's actually in decimal. 3 tambah 6 is 9, but then now we only in base 8, so we minus 8. Jadi 1 and another one yang carry 2. Jadi kat sini for the next column. So the answer is 1, 1 base 8. Okay. We can perform addition and subtraction in octal and hexadecimal. Just the same that we did for binary and decimal number. Okay, we carry the same rules. Okay, for octal addition, the rule is once the summation of two numbers is greater than 8, then we carry over 1 to the next column. Yang ni lah. Okay, and the number of existing column is the summation minus 8 with subtraction being done in decimal system. Okay, first 3 plus 6, we get 9. 9 minus 8. Why? Because it is in base 8 for octal. Okay, and we have carry 1 kat sini lah. Okay, for example, we have cuba buat 73. 73 base 8 plus with 6 base 8. Okay, the example will be 101 base 8. 73 tambah 6. Both in base 8. Jawapan dia akan dapat 101 to the base of 8. Okay. Okay, next we go for subtracting from 73, meaning that 73 minus 56. Okay, for octal subtraction, the same borrow rules apply. In decimal, we may recall that each time we borrow 10. However, in octal, each time we borrow, we only borrow 8 because it is base 8. 3 minus 6 cannot, so we borrow from 7. Kat sini, meaning that we borrow 8. So, 3 tambah dengan 8. We already have 3, then we borrow 8. 3 we add with 8 that we borrow, so it will become 11 lah. So 11 minus 6. So that is how we get 5. Okay. This is for the first column. And for this column, initially 7, but we already borrow 1, so dia akan jadi 6. So 6 minus 5, so dia akan jadi 1. So this is the answer, 1, 5 base 8. Alright. Try to do, for example, 312 base 8 minus 64. 312 minus 64. Is it boleh dapat 226? Dapat tak 226 base 8? Okay, for another one, we have hexadecimal. For hexadecimal subtraction, we apply same borrow rule for octal, and then the step is the same, but then since it is base 16 for hexa, remember hexa is base 16, then we borrow 16 lah from the previous or the next column. Okay. Okay, we have learned the technique of how to perform arithmetic addition and subtraction. And for the various number system, which also included the fractional number addition. Okay, to be in binary point, decimal point, or octal point, fractional number. Next, we go for representation of negative number. Okay, so far in our study of binary arithmetic, we have only considered positive number. Now, we need a way to represent sign of negative number. Let's say we have minus 0.953 base 10 or minus 32 base 10. Okay, when we do computations in decimal, we simply attach a minus sign to the front of a number to make the number negative. Since the computer can only work with bits with 0 and 1, we need to modify the approach slightly. Okay. We have first complements and second complement. Okay, a way to represent a negative number in binary is to add an extra digit to the front to our binary number to indicate whether the number is positive or negative. Remember that a bit is simply another name for a binary digit. Okay, we refer as a sign bit. Okay, the added bit is a sign bit. For a positive number, we can make sign bit 0 and negative sign bit 1. Okay, this is very similar to adding minus or positive sign in decimal. Okay, there is a problem with the sign magnitude representation. Okay, the number of bits in a number must be known so that we can be certain which bits is represent the sign for the magnitude representation. Okay, first complement, we do this by changing all the bits that are 1 to 0 and all the bits that are 0 to 1. Meaning that we change 1 jadi 0, 0 jadi 1. This is called complementing a number. Note that we have padded only number with less than 3 digits with 0 to make it a 3-digit number. In this 4-bit sign magnitude representation that we are using, we know that the first bit is our sign and the remaining 3 bits are the number. If we did not know that we are using a 4-bit sign magnitude representation, then we would have thought, let's say, 1101 to the power of 2 is actually number of 13 base 10. So we have to be careful lah which one is the sign bit. There are ways of representing negative number in binary system that would allow us to change subtraction to addition operation. In the binary system, we can do this by representing negative number as complements. Then we will look at 2 ways of represent number of using complement with first complement and second complement. Okay, this for first complement. Let's say for example, we have positive 5, base 10 is 0, 1, 0, 1. Okay, if it is negative 5 base 10, it's going to be 1, 0, 1, 0. We change all the bits accordingly. 1, 0, 1, 0. Okay, this is for first complement lah. Okay, there is 2 steps. We write the positive value of the number in binary, then must be 4 digits since we are using 4-bit representation. Okay, change to 4-bit. For the left foremost digit, we pad with 0. Okay, let's say initially we have 101, then we add with 0 to make it 4 digit, and next we reverse each bit of the number so that 0 become 1 and 1 become 0. That is how we can get 1010. Okay, this is for negative 5 base 10. Okay, next we have second complement. Okay, for second complement scheme, added a 1 base 2 after complementing the number. For example, we have 5 base 10. This is value in positive. Okay, for negative 5 base 10, this is actually minus 5. Then we can write by this one. Okay, this 0. Okay, we add 1. So dia akan jadi 1011. Okay, this is for second complement. Meaning that we have to know it is either first or second complement. For a signed number in the second complement scheme, we merely take a first complement by add 1 to it. Then we use minus 5 again kat sini to show how this is done for a 4-bit representation. Okay, first write positive to binary. Jadi 0101 and then reverse each bit 0101, then it will become 1010. Okay, 1010, and then we add with 1 bit. Okay, we add with 1 bit 1010, add dengan 1, that akan jadi 1011. Okay. It is for second complement. Okay, we see in the table for first and second complement. Okay, there is one way to represent 0 in the second complement scheme. This is desirable since it simplifies the representation of signed number, as with first complement, only negative value need to be complement. The positive value are the same as the normal binary number. Okay, let's say we want to do subtracting in first and second complement. Okay, we shall now show how the first and second complement system can be used to convert subtracting problems to addition. Okay, perform the addition like this one kat sini. It is actually minus kan. Okay, so kita tukar terjadi plus kat sini. Okay, for example here. Okay. The first complement we have look as the step. Okay, we have 1, 2, 3. The first complement representation has a drawback. 2 additional steps are required after each computation. Check for an overflow bit, and if overflow exists, add the extra bit to the results for correct answer. With second complement, nothing else need to be done. We just throw out the extra bit with no further computations necessary. The second complement's representation is definitely a better way. Okay, we compare one by one. Let's say we want to convert 3 base 10 to minus 3. If it is in first complement, it is actually 0, 0, 1, 1. Kan? Kalau 3, dia akan jadi 0, 0, 1, 1. So, first complement, we convert 0 jadi 1. 0 become 1 and 1 become 0. So, it will be from 0, 0, 1, 1, it will be 1, 1, 0, 0. Okay? And for first complement. And for second complement from 1, 1, 0, 0, then we add with another 1 bit. 1, 1, 0, 0 tambah dengan 1 bit, dia akan jadi 1, 1, 0, 1. Okay, that's for second complement. Then if you want to perform addition, okay, this is for second and first complement. Okay, this is for 10. Sorry, this is for 9 base 10. 9 base 10 is 1001. Okay. And this is the value minus 3 in second complement, and this is the value for minus 3 in first complement. So just perform the addition je lah. Okay. For second complement, this card overflow bit, let's say we have 0, 1, 1, 0, it will become the 6 in base 10. Okay. For first complement, then we add the overflow bit to the right foremost. Kita tambahkan dekat sini. That is how we can get 0, 1, 1, 0. Okay, the last step is necessary if there is an overflow bit. Otherwise, we will not get the correct answer. Okay, that's the comparison for first and second complement. Next, we go for logic gates. In logic gates, we are dealing with condition, 2 conditions only, either true or false. Okay, there is no between true or false, slightly true or slightly false. No, there is no such condition. We can represent condition that we are testing for truth or falsity by symbol. Okay, in regular mathematics, they are labeled as variables. Okay. For instance, the statement the machine is on, okay, might be represented by symbol A. If the machine is really on and A is true, then we can write. Otherwise, the statement is false. Okay, this sort of logic made life easy. Okay, does it? We can represent the off condition. Okay, let's say for this one, A is machine is on. Okay, if A bar meaning that machine is off. Okay, we represent the off condition of the machine by A bar. Okay, A and A bar also we call as the logic states in digital electronics. Okay, for true and false, also we can write in A and A bar. Okay, and also in bit 1 and 0. Okay, 1 is for true, 0 is for false. So now we can see why the binary number system is important for this logic scheme. In logic electronics, this true and false condition may be represented by electrical signal. For example, true condition we can represent by high voltage level. High voltage level, it is equivalent to by 1 lah. Okay, for low voltage level, false, it is 0. Okay, if the statement the machine is on is false, then the statement the machine is not on must be true. Okay, the latter condition we call as the complement for the former statement. Okay, in Boolean algebra, a complement is defined as opposite or negative form of the original statement or the variables. Okay, for example, if machine is on, then the statement the machine is off would be false. Okay, as mentioned, we can write as A or A bar lah for on and off condition. Positive and negative logic. Dealing with the voltage level in electronics, there are polarity involved, either positive or negative, which is logic polarity. Okay, what is different between positive and negative logic, and what is high and low voltage from electrical perspective? Okay, when we say that high state is assigned a value of 1, then assign a value of 1 to a high voltage state and 0 for low state. Okay, we're using positive logic. Many variations are possible from a high positive to a lower positive voltage. For example, high is equivalent to 10 volt and low is 3 volt. Or from positive voltage to ground. Let's say high is we set is 5 and low is 0 because ground kan. Or from high negative to a low negative. Or from ground to negative. Okay, ground to more negative. Okay, kalau ground to more negative, it might be from 0 volt to minus 3. Okay, for low is minus 3. Okay, like this one. Okay, this is from ground to negative 0 to minus 3. Okay, from high negative to low negative minus 2 to minus 8. Okay, in positive logic, the first state is at a more positive voltage level than 0 state. Okay, the state 1 is more positive voltage than 0 state. Based on the discussion, then we can deduce that a negative logic, the one state is not a voltage level more negative than 0 state. Okay. Okay, now we have AND gate. Okay, this is AND gate with two input A and B and X output. Okay, this is the first gate that we should know. It is a logic circuit that requires all input to be true at the same time in order for the output to be true. Okay, we have two input and we use the mathematical statement X is equivalent to X equals to A and B or X equals to A dot B. Okay. This is the standard symbol. Only when both input A and B are high, then the output will be high. If it is 1 and 1, 1.1 equivalent to 1. Okay, if 1.0 is equals to 0, 0.1 equals to 0, 0.0 equals to 0. Okay, let's see. And truth table. This is truth table for AND gate. And now we have 3 input. We can have 3, 4, 5 inputs. Okay. We have input A, B, and C, and X is the output. Okay, the truth table gives all the possible input at A, B, and C input and corresponding output at X. Okay, we can actually have the AND gate with more than 2 inputs, and for multiple input, all the input must be high or 1. Okay, to get the output 1. Okay, let's see. Okay, in general, an AND gates must have with n number of input with 2 to the power of n possible combination. Like here, we have 3 input, n is 3, 2 power n. 2 kuasa 3 is equals to 8 output. Okay, kat sini betul tak kita ada 8 output? Okay, kan? 8 output. Okay, for a multiple input AND gate, in order to produce a 1 output, all the inputs must set to 1. If any or all the inputs are 0, then the output is 0. Betul tak? If we want to get output 1, so all the input must be 1. 1, 1, 1, 1. If one of the input is 0, then the output will be 0. Why? Because this is with dot. Dot ni macam darab lah, multiply kan? Okay. So that's for AND gate. Next we have OR gate. Okay, OR we can write by this one. x equals to a plus b. We have two input here. Okay, the OR gate needs only one input to be high in order to produce a high output. Or we can say that any high output will yield a high input will yield a high output. 1, 0 jadi 1. 0, 1, 1. 0, 0, 0, 1, 1, 1. Okay, if more than 2 inputs, then we have A, B, C and D. Katakanlah lah, yeah. If we have 3 inputs, A plus B plus C. Okay, or 4 inputs, A plus B plus C plus D. Okay. Okay, for multiple inputs or gate, as long as one input is high, then the output will be high. Okay, so that's for OR. And for NOT gate, NOT is inverter gate. Okay, inverter gate or complement gate. Okay, we refer as NOT gate. Okay, the logic device should take the input and inverts this input as the output. Okay, if input is high, then dia akan jadi vice versa lah. Okay, if it is, this is how to write the x equals to A bar. Okay, 1 jadi 0, 0 jadi 1. Okay, that's for NOT gate. Next we have NAND gate. Okay, next we have NAND gate. Okay, the NAND gate is a combination of two logic operation AND and NOT. Okay, this is the AND gate. We have AND with the NOT gate. So that can ada one dot here lah. How to write x equals to A dot B bar. Okay, this is for NAND gate. For input A and B, if either A or B are low, then the output will be high. The vice versa from the AND gate. The next one we have NOR gate. Okay, the NOR gate is made from OR and NOT. Okay, OR and NOT. How to write x equals to A plus B bar. Okay, NOR gate is an OR gate with an inverter on the output. Okay, NOR gate will have a high output when all the input are low. When both input to the OR gate are 0, then the output of gate is 0. But we have the inverter, so the input will be 1. Okay, dia terbalik dari OR gate. Okay, next one we have exclusive OR gate. Okay, how to write the exclusive OR gate? This is corresponding Boolean function x equals to A plus circle B. Okay, the exclusive OR, or we can write XOR. XOR gate is a modification, okay, from an OR gate. Modification of OR gate. The XOR gate produce one output only when one of the input is 1. Okay, when both input are 1 or both are 0, then output is 0. Let's say if we have 0, 0, it will become 0. 1, 1 is also 0. 0, 1, output 1. 1, 0, output 1. Okay, that's for truth table of the exclusive OR gate. Okay, next we go for gate universality. Okay, for gate universality, we have NAND and NOR gates are special in that they can be used to construct any of the other gates, and the ability of single gate type to be able to mimic any other gate type is one employed only by the NAND and the NOR. Okay, in fact, the digital control system have been designed around nothing else but NAND or NOR gates, with all the necessary logic functions being derived from the NAND or the NOR. Okay, we have NOT gate can be constructed using NAND or NOR gate. Okay, the NOT gate can be constructed using only NAND or NOR gate. We could verify with appropriate input that indeed that the way the gates connected does indeed make them NOT gate. Okay, this is the implementation of NOT function using the NAND and NOR gate. Okay, let's say we have an input for NAND gate. This is for NOR gate. Okay, and we can connect with the VCC. This is supply and this is for ground. Okay. When we want to constructing the AND gate, okay, we have two input, A and B. Okay, for here, if it is 1, 0, okay, let's say if it is 1, 1. Okay, if it is 1, 1, dia akan jadi here is 0 because it is ada converter kan, ada inverter kat sini. So it is 1, 1, we will have 0 here. So if it is 0, bila dia masuk, dia akan jadi kat sini, kita akan dapat 1. Okay. That is for NAND gate. Okay, implementation of AND function using NAND and NOR. This is to implement. This is using NOR function. Okay, to do the same using NOR gate, we let the two input A and B to go through the NOT gate. Implemented using the NOR gate. The output from each of these NOT gate for, let's say, 1, 1, we have 1. And here will be 0, so here will be 1. Okay, the two input of state 0, then the single for NOR gate produce output. Let's say here 1, 1, it will become 1, but then we will get 0. Okay, produce the output. Okay, this is so constructing the OR function. Okay, the implementation of a function using NAND and NOR gate. This is how to get NAND and NOR gate. Okay. Okay, the OR gate can be easily implemented using NOR gate. All that is required is to invert the output of the NOR gate. Okay, the first is by using NAND gate, and this is by using NOR gate. Okay, using NAND gate, we must invert all input to mimic the OR function. Okay. To get the OR function. This is quite famous question to be asked dekat dalam course assessment pun normally ada soalan on this juga. Okay, constructing the function logic gate. Next, we want to construct the NOR function. We can construct an OR out of NAND. Okay, then it is simple method to invert the OR output to obtain a NOR gate. Okay, using NAND gate. We want to get NOR by using the NAND gate. Next one. Okay, next one, we want to construct NAND function by using the NOR gate. Okay, we want to get NAND function by using the NOR gate. Okay, to construct the NAND function using NOR gate, we must invert all inputs to the NOR gate as well as the NOR gate's output. Here we use 4 NOR gates to get the NAND function. Okay, you have to go through one by one input to the output and to the next stage of the gates to get the final answer for the construction. Okay. Okay, that's all for the slides of Unit 1. Is there any question from you guys? Okay, to do some exercise, you guys can go to the course schedule, study schedule. Okay, study schedule here. Sekejap ya, I share. Okay, you guys can go to FlexLearn study schedule. There will be self-learning activities here. Okay, you guys can try. Ada video juga. Okay, try to do all for the unit 1 first. Okay, this is course assessment question. Okay, you guys can try to complete the question. Let's say for ni macam soalan yang kita discuss tadi. Okay, question 1 dah boleh try buat, and question 2 okay, can try. Same goes with 2, 1B, 2A, 2B pun dah boleh buat. Okay. Okay, try to do first, and then if you have any question, then you may WhatsApp saya. Boleh WhatsApp je. And you may also show to me your answer to verify either correct or wrong lah. Okay, for your answer. Okay, is there any question? Is there any question from you guys?
At the moment, no.
Alright, thank you. Okay, before you leave the session, please write down your name for the attendance. Okay, thank you. I think that's all. Kalau tak ada soalan, then that's all from me. And please do not hesitate untuk WhatsApp saya, tanyalah if you have any question. Alright. So, apa lagi? I think that's all for this class today. Alright. So, thank you guys.
Thank you.
Okay, thank you,
Alright,
Doctor.
so bye.
Yeah,
Bye.
Thank you.
Thank you. Bye-bye.
Okay, bye.